So welcome back on the GATE Academy English channel. Okay, we are here to continue with our series of gas turbines and steam turbines. We are here to continue with the series of the gas turbine and steam turbine. Okay, okay, which is our newly added topic in GATE 2021 syllabus. Okay, so we have completed some sessions already. Okay, so if you are new to this session or if you are seeing this video for the first time in this lecture series, please go and watch all the other sessions of this series. Okay, then you will be having the better idea. For that, I will request you to subscribe the GATE Academy channels. Okay, so before continuing, let me tell you who am I. Who am I? So, my dear students, my name is Umashakar Tripathi. As you can see on the screen, we are here to continue with our lecture series of steam and gas turbine. Steam and gas turbine. Okay. So, my name is Umashakar Tripathi, as you can see on the screen, and I am currently a PhD scholar at IIT Roorkee. PhD scholar, you guys usually people call us as research scholar. Okay. So, before getting into this PhD thing, I have completed my MTech from IIT Roorkee itself, and as far as the GATE examination is concerned, I have given GATE 2014 and 15. So in 14, I had 65.66 marks with All India rank of 916. And on the basis of that, I took admission in the master's program of IIT Roorkee. Okay. In 2015, my marks was 77.02 and I had an All India rank of 643. Okay. So from the last 8+ years, I have been into this GATE coaching. Okay. So as you know, the GATE Academy is having 50+ centers across India. So we used to teach at those centers, offline centers, before this lockdown period. Okay. So in this lecture series, we are here. Where we are? We are at this point. We are at this point. Okay. Till this we have completed. We have completed the steam turbine in all respects. We have completed the steam turbines in all respects. Okay. Now we are going to continue with our Brayton cycle. Okay. We were seeing the gas turbine section. So for that, we are going to see our Brayton cycle. In the last session, we have left at this point. Let us open it. So we have left where? Okay. So where we were at, just a moment. Okay. So we were here. We were developing the efficiency of Brayton cycle. We were developing the efficiency of ideal Brayton cycle. And what would be the approach of the further sessions remaining that we have seen? Steam turbines in all the respects. So gas turbine velocity triangles, efficiency formulas are not required to be seen again because we are already okay with this bleeding and all. Everything we are comfortable in. Okay. So here we are trying to make space for understanding the actual gas turbine cycle. You might have been thinking, sir, this ideal Brayton cycle was already there on the syllabus. So yes, it is already there on the syllabus. No problem in that. But we are trying to learn actual gas turbine cycle as well. So for that, we are trying to understand this ideal Brayton cycle. Okay, so we are going to move ahead. So in this, what we have seen this is the TS diagram of our ideal gas Brayton cycle. Okay, from here we can say the efficiency is turbine work minus compressor work upon heat added. And turbine work we have derived from steady flow energy equation as H3 minus H4, and from a steady flow energy equation again we have derived the compressor work to be equal to H2 minus H1, and our heat addition that is input to this cycle is H3 minus H2. Now using this fundamental equation of H is equal to CPT, as H is equal to CPT, which we can use comfortably for ideal gas, we have converted all these enthalpy values in terms of temperature. So from this we can find the efficiency of ideal Brayton cycle in terms of temperature. So let's say if we have a question and we can find the temperatures at all the points, within the cycle, we can solve for the efficiency right here with this equation, right? With this equation, okay? But we need to see it, we want to see it in terms of pressure as well, So let's try to do it. So can I rearrange this equation? We are continuing here where we have left from in the last session. If you have not seen it, please go and see it. Then only you will have some better idea. Then only you will have the better idea about this topic, what we are running here. So from here we can see this is T3 minus T2. We can write like this: T3 minus T2 minus T4 minus T1. I am just rearranging it a bit. So this is T3 minus T2. This is T3 minus T2 again. So can we rewrite this like this? 1 minus T4 minus T1 upon T3 minus T2, T3 minus T2, T3 minus T2. We can write like this. Is there any problem in that? Tell me, is there any problem in that? No problem. Okay. So now, as we know, the live student can respond to me. As we know that the process of compression and expansion is completely isentropic. So can we write like this? T4 by T3 is equal to P4 by P3. All right, to the power gamma minus 1 by gamma. Okay, we have seen all this in this series while we were discussing the compressible flow also. Okay, in this series only we have completed the compressible flow also. So this series is very, very useful for the aspirants who are preparing for 2021 examination, 2021 GATE examination. So we have this P4 by T3 is equal to P4 by P3 to the power gamma minus 1 by gamma, and also we can write like this. That T1 by T2 is equal to P1 by P2 to the power gamma minus 1 by gamma. All right. So from here, if you see this TS diagram, see this TS diagram, can we say P3 is equal to P2? We have also seen this in PV diagram here also. So you can say P2, P3 are equal, and similarly P1, P4 are also equal. So let me introduce a term that is pressure ratio. So let me name this pressure ratio as RP. So pressure ratio is higher pressure by lower pressure. So we can call it as P3 by P4, or we may call it as P2 by P1, because as you know, as I have said, P3, see in Brayton cycle, P3, P2 or P2, P3, whatever you may want to say, you can say it, and P4, P1, both are equal. You can see it here in the TS diagram. This is the same constant pressure line. It is also the same constant pressure line. And we can see it from our PV diagram as well. Okay. So can we say this pressure ratio is high pressure by low pressure? So if I replace this in these two equations, we can write like this: 1 by Rp to the power gamma minus 1 by gamma, and this can be written like this: Rp gamma minus 1 by gamma. Okay, can we do it? So certainly yes, we can do it. So from this you can see in this equation right hand side is equal. So can we write like this? So T4 by T3 is equal to T1 by T2 Okay. Sometimes in order to do the question quickly, we require this kind of things. So from here we can say, I have just highlighted it because it's a very useful thing, and already we know all these things, but I am highlighting it because this is important. This is what we are going to use. And you can say, it from here that sir, both of this are equal to the same thing, and that is equal to rp to the power gamma minus 1 by gamma, rp to the power gamma minus 1 by gamma. So from the concept of componendo and dividendo, we have seen the componendo dividendo far when we were small kids and studying in the school. We have seen something like componendo dividendo. So you can do some more mathematics, but to do it quickly, I apply a concept of componendo dividendo. So componendo dividendo, what componendo dividendo tell us? If a by b is x and c by d is also x, so the difference between numerator of these two and denominator of these two and their ratio means a minus c divided by b minus d will also be equal to x, So if you observe, same kind of thing is happening here. See, T4 is here, T4 is here, T1 is here, T1 is here, T3 is here, T2 is here. So let me directly use this concept of componendo dividendo. Componendo dividendo, we can find the efficiency, and it is coming out to be, this difference will come out to be x. So 1 upon 1 minus rp to the power gamma minus 1 by gamma. Can we say like this, rp ki power gamma minus 1 by gamma? So this is what is the efficiency equation in terms of pressure ratio, of ideal gas turbine cycle, or we can say ideal Brayton cycle. What we can say it, we can call it that this is the expression for efficiency of ideal Brayton cycle. Is that clear to all of you or not? How we have derived it? The students who are live in this session can reply to me. Is that clear how we found the efficiency of ideal Brayton cycle? So if we have this pressure ratio, if we have the pressure ratio, we can directly find out the efficiency. Of ideal Brayton cycle. All right. Okay. So from this, can we have some observations too? So if I increase the pressure ratio, can I say my efficiency will also going to be increased from this relation? If we increase this term, so definitely this term will be decreased and this term will be increased. So from in ideal Brayton cycle only, so this is exclusively, this information is exclusive for ideal Brayton cycle. We are talking about. So if for ideal Brayton cycle, if we talk, so we can say that with increase of pressure ratio, we can have the efficiency also increase. We can have the increased efficiency also. So if pressure ratio is increasing, our efficiency is also increasing in ideal Brayton cycle only. So with respect to any cycle, as we have now seen all these things in the steam turbine scene, we have studied about the device, the steam turbine as an equipment, and now here we are trying to see the cycle. So from the concept what we are building here, you can directly apply to the Rankine cycle as well. So now see, there are some terms that can be defined with respect to any power cycle. So few terms let me describe, and then we'll move ahead. We are trying to cover as much as possible in this session about the ideal Brayton cycle. So we are going to see most of the thing with respect to the cycle in this session, and in the next session we may have some questions solved of it, and then we'll move to the actual gas turbine cycle. In the last session, we will see the components of the gas turbine, and we will just summarize this series, and then we will end this series. So after this session, 2 sessions more will be left. That will happen on tomorrow, and then we will have this series finished. Okay. So there is a term called back work ratio. So it is defined as negative work in a cycle. It is defined something like this. negative work in a cycle upon positive work in the cycle. Positive work in a cycle. Upon positive work in a cycle. Okay. So our back work ratio is what? A back work ratio is negative work in the cycle upon the positive work in the cycle. So in a cycle, you have to identify the negative work. So in this cycle, we have seen where is our cycle. This is the cycle we are having. So this is the ideal gas turbine cycle or Brayton cycle, as we may want to call it. So in this, compressor is the device in which we have to supply some work. So in this negative work is compressor work. Negative work is compressor work. Okay, so we can say negative work in the cycle is compressor work, and positive work is turbine work. Positive work is turbine work. So we will having our back work ratio. This kind of terms sometimes asked in gate examination. Okay, so now there is another term. Let me define that also. There is another term. We can define that also. We can define that also. So we have one thing called as work ratio. We can have one thing called as work ratio. Work ratio. Okay, work ratio. So this work ratio is nothing but the net work in a cycle. The net work in a cycle. Okay, in a cycle upon the positive work in a cycle. Upon the positive work in a cycle. Okay, so we can say that that network is turbine minus compressor, and the positive work in a cycle is turbine work. So from here we can say our work ratio is 1 minus back work ratio, 1 minus back work ratio, 1 minus back work ratio. So work ratio is nothing but 1 minus back work ratio. Okay, 1 minus back work ratio. So higher the back work ratio, lower will be the work ratio. Lower will be the work ratio. So you have seen, if we talk about in general, you might have seen that steam power plants are more in use in power generation, more dominating in power generation. So this is because the fact that in gas turbines, as I have told you in the previous session also, in gas turbine cycle, what happened? The amount of work which is developed by turbine, almost 40 to 50% of that work is consumed by the compressor. So we have we have high back work ratio in gas turbine cycles, and lower work ratios in gas turbine cycle. While if we talk about the steam turbine cycle, in place of compressor, you have seen there is pump. In place of compressor, if you see, there is pump. So pump require less energy to operate. Pump require less work as compared to as pump require less work as compared to the compressor. So in a steam turbine cycles, the work consumed by the pump is very less as compared to that of gas turbine cycle. Okay, so in a steam turbine, our back work ratio in a steam turbines, our back work ratio in a steam turbine, our back work ratio is low and work ratio is high if you compare it with gas turbine cycles. So that's why in power generation, most of the time steam turbines are in use. All right, got this point? Got this point or not? So from this discussion, you will be able to calculate the back work ratio as well as the work ratio. Okay. Now we have to see something else also here. Is that clear? The live students can respond to me. So let's understand a few more fundamentals here. So effect of pressure ratio. Effect of pressure ratio. Effect of pressure ratio on the efficiency of the effect of pressure ratio on the efficiency of Brayton cycle, on the efficiency of Brayton cycle. So what is the effect of this pressure ratio on the efficiency of Brayton cycle? So you will say, sir, we have seen it. If we increase the pressure ratio, you just have told us here that if pressure ratio is increased, our efficiency will increase. But this is not that simple. This is not that simple. Now we have to understand few more things here. So if I do it by using, if I try to show you by using our TS diagram, just let us pay a little more attention here. In this lecture, we are describing you about the Brayton cycle, the basics of Brayton cycle. Okay, the basics of Brayton cycle. We are not going to do any example in this class, but we will establish all the concepts of the Brayton cycle so that we can easily understand when in next session we see the actual gas turbine cycle. So we can have a comparative talk about it, and then we'll solve few examples also. So we have this TS diagram. We will have this TS diagram. So in a TS diagram, what happens? So let's say I have these two pressure lines. This is lower pressure. This is lower pressure. This is, let's say, lower pressure. This is, let's say, higher pressure. This is, let's say, higher pressure. Okay, this is, let's say, higher pressure. Okay, so if I tell you something, I hope you all will be able to understand. So while analyzing a cycle, it is of any material, it is definitely all the components are built up of a material. So can we say, yes, sir, we have a limit on, this maximum temperature. We have a limit on this maximum temperature. Say yes or no. We have a limit of this maximum temperature. Yes or no? Yes or no? So the temperature in the cycle cannot be increased beyond this point. The temperature of the cycle cannot be increased beyond this point. So if you see the TS diagram, so the temperature is maximum. The temperature you can observe here in the general TS diagram, what we have developed in the previous session. So in this TS diagram, you can observe that the temperature in gas turbine cycle or Brayton cycle is highest after the gas or air, after the gas or air leaves the combustion chamber, because there in the combustion chamber some heat will be added into it. So much of heat is added in the combustion chamber. So at the exit of the combustion chamber, or you can say before the entry to the gas turbine, the temperature is higher. So now I am saying that this highest temperature will have some limits, because every material has a limit on temperature. Is that true or not? Live students can respond to me. Is it true or not? Is it true or not? Tell me. Is it true or not? Live student can respond, please. Every material has this limit of temperature, maximum temperature. Okay. So now if I increase, if I say, so let's say this is our two pressure lines. This is our two pressure lines. So if I compress what? If I compress the air in the compressor, if I compress the air in the compressor, will go to this pressure. This is P2. This is P2. And now you will do the heat addition. So you cannot go beyond this point. You cannot go beyond this point. All right. You cannot go beyond this point. So you will have to expand from this point. So you will make the air enter to the gas turbine at this point, and it will leave the turbine at 4 and will enter the cooler, and again it will come to the temperature 1. Again it will come to the temperature 1. So let us limit this also. Let us limit this minimum temperature also. let us limit this minimum temperature thing also. Why we are limiting this minimum temperature thing? Because we require to compare. And also more or less this is an aircraft cycle. So we are taking the atmospheric here. We are taking mostly, if it is not a closed cycle, we are taking the atmospheric air inside. Okay, so the temperature of atmospheric air more or less is constant. More or less is constant. So I am fixing this also. Okay, so if you find the efficiency of it, let me write the formula here. So this is the formula. This is the formula. Okay, so this is the formula of efficiency we have developed of the ideal gas turbine cycle. So let us say the efficiency of this first cycle is N1. Efficiency of this first cycle is N1. Its first cycle is N1. So now let me increase a pressure. We can increase the pressure ratio. So if I increase the pressure ratio, so let's say I am now going to compress my air to this pressure, to let's say this pressure, and let's call this pressure as 2 dash. Let's call this pressure as 2 dash. So if I add some heat, if I add some heat, I will go to this point. Can I go beyond this point? So yes, no, I cannot go beyond this point because this is the temperature limit we are having. Our cycle cannot go beyond this temperature, so we have to stop here. So we will do the expansion isentropically, and we will reach to this point 4 dash, and our cycle will be 1 2 dash 3 dash 4 dash. So if you compare these two cycles, if you make a little bit comparison between these two cycles, you can say, sir, in efficiency, when we were talking about our first cycle, the red pen one cycle, the cycle which is in red pen, sir, which is the red pen cycle here, 2 to 3 also. This is the red pen cycle, no? Getting my point? So our efficiency in this one section is RP1. The pressure ratio is RP1. The pressure ratio is RP1. And at this second cycle of this blue pen, let's say efficiency is 2. We have our pressure ratio as RP2. So you can say certainly from here, sir, that RP2, let's say, so our pressure ratio of cycle 2 is greater than the pressure ratio of cycle 1. So we can say the efficiency of cycle 2 will definitely be greater than efficiency of cycle 1. Is that true or not? Because we have established this fact that pressure ratio if higher, and from the formula written in the black ink, you can comment that, sir, in the case 2 we have the efficiency higher. We have this higher efficiency. Even if you don't want to see from the pressure ratio, you can see by second law of thermodynamics, Carnot principle. You can see it by Carnot cycle also. See, let us do it. Let us try to see it or observe it by using Carnot cycle also. So what is the reversible efficiency if you apply? What is the reversible efficiency if you apply the Carnot principle? So if it is TL by TH, means higher temperature 1 minus lower temperature by higher temperature in general. So can I say like this? Now see, I am writing it here. So can I see the reversible efficiency is 1 minus TMR and TMA. So what is this TMR stands for? So this TMR is mean temperature of heat rejection. Mean temperature of heat rejection, and let us call it mean temperature of heat addition. So what happens in a Carnot cycle? I hope you all know or heard about this Carnot cycle. So in Carnot cycle, this temperature of heat rejection is constant because the process is isothermal, and the temperature of heat addition is also constant. The process is isothermal again. But here in any other cycle, like as you see in a Brayton cycle, the temperature is not constant, so we can compare it by using the mean temperature of heat rejection and mean temperature of heat addition. So let's just do one more thing here. So if I say that TMR is reducing, if in some case from this formula is mean temperature, if mean temperature of heat rejection decreases, efficiency increases. Efficiency increases, can we say like this? And mean temperature of heat addition, mean temperature of heat addition, if increases, the efficiency decreases, the efficiency again increases. Okay, so how I am using it? When you are asking, sir, how mean temperature we are using? Now see, you will be able to understand from here, but can you respond? This is the reversible efficiency, Carnot efficiency you call it. So what is the role of Carnot engine in our thermodynamics? You must have read, you must have read that Carnot cycle is not a practically used cycle. It is a reversible cycle, so we cannot use it because it has two isothermal processes, and we know isothermal processes are those which are infinitely slow, slow. So practically, Carnot cycle is not of any use. So why we study Carnot cycle? How it gains so much limelight in the field of thermodynamics? Why it is so much important? Because it is a cycle which has maximum possible efficiency between these two temperature limits. Also, this is a cycle which we use to compare with the other cycles. This is the cycle which we can use to see how other cycles are performing, or it is a cycle which is used to make comparisons mostly. So this is what I am trying to do. I am trying to relate, and this fundamentally you can apply in any cycle. Otto cycle, diesel cycle, Rankine cycle. So we can compare the efficiency of all the cycles with the Carnot cycle. Okay. So why I have written this mean temperature or average temperature? Because in any other cycle except the Carnot cycle, heat addition, heat rejection do not take place at constant temperature. Yes or no? Heat addition, heat rejection do not take place at constant temperature. So as the temperature is not constant, I am taking a mean. Mean means what? That we can assume that heat addition is taking place at this mean temperature. Got my point, Pawan? Yes or no? It will be more clear by seeing this example, by seeing this cycle. Now see in this red pen cycle. Trying to compare these two. So if we say this is a TS diagram. So from 2 to 3, if you observe, the mean temperature will be somewhere in between 2 and 3. Average is somewhere in between, na? It is somewhere in between, na? So in between 2 and 3, this is our mean temperature of heat addition. This is our mean temperature of heat addition. Is it or not? Mean is what? Somewhere in middle of the two values we are having. This is what we call average or mean. No, in general. So as compared to this red pen mean temperature, our new cycle 2-3-. So what is happening? 2-3-. Mean will be somewhere in between 2- to 3-. Mean will be somewhere in between 2- to 3-. So I am highlighting it. So this is my let's say this is my TMA2. This is my TMA2, and this is my TMA1. So in comparison to TMA1, can we say in comparison to TMA1 means mean temperature of heat addition in the first cycle, in comparison to the first cycle, can we say by increasing the pressure ratio, the mean temperature of heat addition increases by We can say by increasing the pressure ratio, the mean temperature of heat addition increases. Is it true or not? Can we say that or not? Can we say that or not? So if you see here, if you write it again, so RP with the increase of pressure ratio, we can say that with the increase of pressure ratio, you can, those who are live can respond that TMA increases, mean temperature of heat addition increases, and hence efficiency also increases. Hence efficiency also increases. You can say by this way also. So why we are taking this mean temperature of heat addition rejection into picture? Because we are going to see this intercooling, reheating, regeneration also. From there you can easily compare, you can easily see that what will happen when we do regeneration, what will its effect, what will be the effect of regeneration on efficiency, what will be the effect of intercooling on the efficiency, what will be the effect of, what will be the effect of reheating, what will be the effect of all of them combined. And not only in this cycle, in any cycle you can see by comparing it with Carnot cycle. Here we are doing nothing, just comparing by the Carnot cycle. Now here pay attention again. If I talk about this red cycle 1 to 4, this is the red cycle 1 to 4. So the mean temperature of heat rejection will be somewhere in between this 1 and 4, will be somewhere in between 1 and 4. So this is what we may call, we may call it as TMA2, we may call it as TMA2, yes or no? We may call it as TMR1, mean temperature of heat rejection, mean temperature of heat rejection of the first cycle, on the first cycle. But if you see, then mean temperature of heat rejection of the other cycle, that is 4 to 1, that is this 4 dash to 1. So we can observe that now our T mean temperature of heat rejection, goes somewhere below and has reached this point. This is nothing but, see, we have 2 points and we are taking average. So our average will be somewhere in between of these 2 points. So we do not have to pick up a scale and do it, but by our conscience we can do it, by our wisdom we can place it, we can assume it somewhere in between 4 dash to 1, somewhere in between 4 dash to 1. So this is my TMR, this is my TMR2. So if you observe in comparison to the first cycle, when we have increased the pressure ratio in the second cycle, our TMA means mean temperature of heat addition increases. Our TMR, that is mean temperature of heat rejection, decreases. Mean temperature of heat rejection decreases. Mean temperature of heat rejection decreases. So can we say, sir, as increase of pressure ratio, our mean temperature of heat addition increases, our mean temperature of heat rejection decreases. So overall effect on efficiency, that efficiency should increase, because both of these factors are helping the efficiency to increase. We can see by this formula. Is that clear or not? How to see this concept, how to see with this mean temperature of heat addition, mean temperature of heat rejection? Yes or no? Yes or no? Yes or no? Now tell me, yes or no? Those who are live can respond. Are they able to get this point or not? Okay. Okay. So we are moving ahead. So we have established this fact by comparing these 2 cycles. We have established this fact by comparing these 2 cycles that if the pressure ratio we increase, if we increase the pressure ratio, the efficiency would increase. What will be the effect on mean temperature of heat addition and mean temperature of heat rejection? That also we have seen now. Now, if I say that I go on increasing the pressure ratio from all these things, all this relation we have seen, that the efficiency of the cycle increases. But can you tell me by what amount we can increase this pressure ratio? we can increase this pressure ratio. By what amount? By what amount? So we can increase this, we can't increase this beyond this point. So this is the maximum possible, this is the maximum possible, this is the maximum possible, possible pressure ratio we can have. Yes or no? This is the maximum. What is our pressure ratio? See what is our pressure ratio? Pressure ratio is T2 by T1. Means or Tmax by T4. Okay. So from here can we say that this is the maximum pressure ratio we can attain. This is the maximum pressure ratio we can attain, and we cannot go beyond this point. So if you see at this RP max, we are definitely going to get the maximum efficiency. So you may feel, sir, this is the best thing we can do. We always want highest efficiency. We always want good efficiency. We always want very, very nice efficiency. Okay. So in order to get, if you are getting very happy that, sir, we are getting the maximum efficiency, so always we must raise the pressure to its maximum possible value by seeing this. So you are wrong, my dear friend, because see, if you raise it, let's say, let us use this grease pan. So if you raise your pressure ratio to maximum possible value, so this line, this line, this line, this line will go like this, this line will go like this, and you will reach to this point. This line will go like this, and you will reach to this point. So let's say this is your 2 double dash. Let's say this is your 2 double dash. So your pressure will reach to this point. Your pressure will reach to this point. That is 2 double dash point. So here, if you are able to get it, so there is no scope. There is no further scope. There is no further scope of heat addition left, because you cannot increase the temperature anymore, because this is the limit of the maximum temperature. This is the limit of maximum temperature. So this RP max is represented by this P2 double dash by P1. So are you able to realize now that if we reach the pressure till this point at 2 double dash, we have no scope left of heat addition. And as you know that the area under TS diagram, if we talk about the ideal cycle, if area under TS diagram is give you the net heat interaction in a cycle, which is in turn by the first law equal to the net work interaction in a cycle. So if we try to get the maximum efficiency, we are getting zero work or almost negligible work. Okay. So now, are you happy? Are you happy or not? That, sir, we have got the maximum efficiency now, but we are not able to get any work from it, or negligible work we are getting from it, because there is no scope of heat addition. There is no scope of heat addition now. There is no scope of heat addition now. So now you see that reaching to the maximum possible pressure is not optimum thing to do. Not optimum thing to do. Although the efficiency is going to get maximum, but our work is going to get negligible or near to zero. Are you able to understand all this thing? So by increasing the pressure ratio, we can say efficiency certainly increase, but when the efficiency becomes maximum, we are getting no work. Out of it. Got my point or not? Tell me yes or no. Got this or not? Got this or not? Got this or not? Okay. So moving ahead. So if we want to find, see, if the pressure ratio goes to its maximum possible, efficiency is max, but work done is going to be almost zero. Work done is going to be almost zero. Okay, work done is going to be almost zero. So now I want to find in what condition or at what pressure ratio condition I want to find in what condition we will get the maximum work, in what condition we are going to get the maximum work, and the condition at which we are going to get the maximum work, the pressure ratio there I will call as RP optimum, optimum pressure, optimum pressure. Okay, so how we can do it? How we can do it? So what is the work? What is the net work? We want to maximize it. So net work is turbine work minus compressor work, turbine work minus compressor work. Is that true or not? Is that true or not? So if we see the cycle, let us bring the Brayton cycle TS diagram over here. So let us copy it. Let us have it copied, and we'll paste it. We'll paste it to that place. Okay, so that we can apply some mathematics on it. We can apply some mathematics now. We can apply some mathematics. Okay, so we are going to apply some mathematics here. So that is why I have copied this figure, so that whatever we are doing, that will be in front of you. That will be in front of you. So we have this net work is equal to turbine minus compressor. We have this work, that work is equal to work of turbine minus compressor. Sir, Pawan, you are asking, sir, specific volume will also decrease by increasing the pressure. So it depends. It depends if you are considered it as compressible or incompressible flow. Okay, because specific volume is changes means density is changing. Density is changing. So if you say the density is changing, then you have to go to the concepts of compressible flow. So if you want to understand about the compressible flow, please view all the lectures of this series, of this session. In the first few lectures, you will get the idea about what to do in the compressible flow case. All right, all right, okay, okay. So whatever changes happen in the specific volume, you may say, will follow the rules of isentropic expansion, constant pressure, heat addition, heat rejection on that. All right, all right. So it is changing mostly. Okay, you can find it by your general relation, and if you are going to get deep into this compressible flow thing, you have to watch the previous lectures. So now continuing from here, so we have this network, is equal to turbine minus compressor. So we know the work in a turbine is Cp T3 minus T4, Cp T3 minus T4, and work of the compressor is Cp T2 minus T1, Cp T2 minus T1, just writing the equation. Okay, so in this, what is constant? You can say, sir, T3 is constant. Why T3 is constant? As we have established, that every cycle has the limit of this maximum temperature. So this T3 is constant. And what else is constant? What else is constant? T1 is also constant. T1 is also not changing. T1 is also not changing. So as we have described you previously also, whenever something of this maximum kind we write, as we have developed the expression of maximum efficiency for impulse turbine, if you remember, for the leveled kind of turbine or one stage of the turbine, we have developed the efficiency of the impulse turbine in this session. We have developed the expression for maximum efficiency of Parsons turbine, 50% reaction turbine in this session. Okay, so I told you what, whenever we talk about this maximum condition or something maximum, if we have to find out, so ultimately we are supposed to go for differentiating. Ultimately we are going to go for the differentiation thing, and later we are going to differentiate it with respect to some variable and going to put it 0, and from here we can get We can get what? From here, we can get the condition in which our said function is maximum. So here we can say if I differentiate this work net expression with respect to the variable and put in 0, I'll be getting the value or the conditions, in which this network is going to get maximum. This network is going to get maximum. Is that clear or not? Okay. So now in this equation, what is the problem we are having? We are having two variables because T2 and T4 both depend upon the pressure ratio what we are having. So we need to reduce this equation to one variable. So for that, can I use this? Expression? Where is this expression? See, I have marked it where this one. Okay, can we use this expression? And can we say, sir, T4 by T3 is equal to, sir, T1 by T2? We can relate now. We can relate the temperature. The ratio of temperatures are the same only. So from here, can we replace T4 in terms of T2? So let's do that. T4 in terms of T2. So this is T1 by T2 into T3, T1 by T2 into T3. So here T1, T3 are constant that we are calling Tmin and Tmax, So we can put it back in this equation. We can put it back in this equation of WNet. So in WNet, if I replace it, so we have this Cp, let's take it common. We have this T3. We have this T4, so let's write T4 is equal to T1 into T3 divided by T2. So T1, T3 are again constant, minus Cp T2. So we have this value of T2 again. We have this value of T2 again. Okay, we have this value of T2 again, and we can say that is plus T1. So this is our work net equation, and here now you can see we are left with only one variable value. We have left with only one variable here. So we can differentiate it. With respect to this T2 and can have the value of T2 in terms of T1, T3. Okay. So let's just differentiate it. So this part will become 0. It will become minus T1 T3 or if we differentiate 1 by T2 will come out to be minus T2 square minus 1 by T2 square minus 1 is equal to 0. The differentiation of T2 is equal to 0. So from here we can say this is T3, this is T3. So I am putting a bracket here and putting a bracket here as well. This is what I have written by differentiating. The differentiation of 1 by T2 is minus 1 by T2 square. I hope all of you know the differentiation of 1 by X. Okay. So from here, can we say this T2 is root of T1 by T3. Okay. And if we use this equation, this formula T4, so we can place the value of T2 here. So if we place the value of T2 here, T4 will also come out to be under root of T1, T3. So what are the observations we are having? So the observation here from what we are observing here, that this T2, T4, if you require to get maximum work, if you want to get maximum work, you should compress or expand your air to the temperature which is geometrical mean of the maximum and minimum temperature, So at this condition, you will get the maximum possible work output. At this condition, you will get the maximum possible work output. maximum possible work output out of our ideal Brayton cycle. Now, if you have calculated it, now you can also calculate the optimum pressure ratio. Optimum pressure ratio means what? At which we are getting our maximum work output. We are getting our maximum work output. So you can say our RP optimum is T2 by T1 is T2 by T1 to the power gamma upon gamma minus 1, gamma upon gamma minus 1. Okay, so if you place the value of T2 here, so T2 is nothing but the geometrical mean of maximum temperature and minimum temperature, geometrical mean of maximum temperature and minimum temperature, and Tmin, T1 is already Tmin, T1 is already Tmin. So can we write like this? Can we write like this? This is gamma upon gamma minus 1, gamma upon gamma minus 1, gamma upon gamma minus 1. So can we write it here? Can we write like this? That's this optimum pressure ratio. This optimum pressure ratio is equal to under root of T max by T min, under root of T max by T min to the power gamma upon gamma minus 1 to the power gamma upon gamma minus 1. So can we write like this? Can we write like this? That our optimum pressure ratio, is is T max by T min to the power gamma upon gamma minus 1, and we can place 1 by 2. Under root means what? 1 by 2. So we are placing 1 by 2 here. So if you see our maximum possible, this is our RP max. No, this is our RP max formula. This is our RP max, maximum possible pressure ratio, to which we can compress it. So if you were compressing to the maximum possible pressure ratio, you would have been getting maximum possible efficiency, but no work you were getting. But if you if you if you if you if you compress if you compress your air to optimum pressure ratio, you are not going to get the maximum efficiency though, but you are going to get the maximum work done. So this play of pressure ratio is clear to you. And in order to find, sir, what maximum work done we are going to get, you can replace the value of T2 in this equation, you will have your answer. So once you get T2 and T4, there is no need of learning or memorizing the formulas. You can go back and place the values of all the temperature what you have in the basic expression of work net. So is that clear? The play of pressure ratio is clear. Play of pressure ratio is clear to you or not? The play of pressure ratio is clear to you or not? Tell me. Tell me. Tell me. Yes or no? Tell me. Tell me. Those students who are live can respond. The play of this pressure ratio is clear to all of you or not? Very nice. So we are moving ahead. So what is this game of pressure ratio? What is this game of pressure ratio? So if we say what is the effect of this pressure ratio? What is the effect of this pressure ratio? The effect of this pressure ratio on the efficiency, on the efficiency, on the efficiency. So efficiency goes on increasing. Efficiency goes on increasing as far as you can increase your pressure ratio. Then there will be a point, there will be a point, there will be a point you are reaching, you got the maximum efficiency, and you cannot increase the pressure ratio above this value. So at this point, you will be getting the maximum efficiency, and you know what is that maximum efficiency? The reversible efficiency, the reversible Carnot efficiency. Okay, but what will happen to the work then? What will happen to the work then? So I am plotting another plot just to make you aware of what is happening or what is the changes are happening with respect to this pressure ratio thing, with respect to this pressure ratio. So if I have the work done on this axis, and if I have the RP on this axis, so we have seen that we have a optimum, we have solved for, just a second, we have solved for this optimum pressure ratio, so the at optimum pressure ratio, the work will be maximum, and at the RP max thing, the work will be 0. The work we are going to get is 0. Okay, so if we plot for the work done, the plot will be somewhat like this, and if we plot the efficiency, it will be somewhat like this. So at RP optimum, you are not getting the maximum efficiency, but the maximum possible work done. So if you increase your pressure ratio beyond this RP optimum, your efficiency will go on increasing, but your net work done in the cycle goes on decreasing. So I think this is clear. The play of pressure ratio is clear. Now let's see the regeneration, the use of, there is some terms. So let us see that use of regeneration. As I said, we are developing our concepts to understand the actual cycle. So we have the use of regeneration. We are going to see now the use of regeneration here. Okay, so in regeneration, what happens? In this regeneration, what is happening? So now let's say we have this TS diagram. So let us copy it again. So from the previous session, I trying to tell you that please make this, or please try to make this T4 temperature greater than T2. Okay, so what is happening? So how is the cycle? What was our cycle? So we had a compressor. Here. This is compressor. So from 1 to 2, the air is coming out from the compressor at 2 point. Then in combustion chamber, heat is getting added. So at 3 point, at the exit of combustion chamber, now it is going to our gas turbine, where it expands, and then there is a cooler. For making the cycle, we always assume a cooler. Here we compare it as a closed cycle. No problem in that. So we are having this cycle. Okay. So now, as you can see, that 4 point represent the exit to the cooler or to the atmosphere. Exit to the atmosphere, we can say. Let's remove this cooler. No problem. We can, while making the cycle, we can assume that cooler. Okay. So now as the air is getting exited from the turbine, it is still having some high temperature. That means when it is having high temperature, that means it is having some high heat energy. Now, if you are letting this air or gas to be get exhausted to the atmosphere, you are somehow wasting this heat energy. So if you are wasting this heat energy as an engineer, you must find a way that we must not waste this energy. We must not waste this energy, and we should convert it into something useful. This is the approach. This is the approach an engineer should have. Yes or no? Yes or no? So as you see that at the exit of turbine, the temperature is still higher. So we can think of utilizing this heat energy. We can think of utilizing this heat energy. So how we will try to utilize this heat energy? So what we are going to do, we are going to, we are going to do something like this. We are going to do something like this. We will convert it path. We will just change the path. So, so the air which was exhausting to the steam, which was exhausting to the steam, now we will apply, we will apply, or we will make our regenerator, which is nothing but simply a heat exchanger. So you can call it as heat exchanger, or you may call it as regenerator. Both are same thing. Regenerator also is a heat exchanger. So in a heat exchanger, what happens? In a heat exchanger, what happens? So now in the heat exchanger, if you see in the heat exchanger, this heat exchanger, what is happening? In this heat exchanger, what is happening? In this heat exchanger, what is happening? That in this heat exchanger, what is happening? So it is happening like this. That's a high temperature exhaust gas are entering from here. High temperature exhaust gas are entering from here, and low temperature air is moving from this green path, and high temperature air exhaust gas is coming from this red path. Okay, so what will happen when they both interact? What will happen when something hot and something cold comes in contact with each other? There will be the transfer of heat. There will be some transfer of heat. So how the heat will transfer? Heat will transfer from high temperature to low temperature, means from the hot fluid to low fluid. So this stream, this exhaust stream of air, this exhausting stream of air will give some of its heat energy to this air going through to this air. Let me say this point A, to this air going through this green path. So what will happen when it will give heat energy to this air? Its temperature will increase. So let me say that the temperature of air before entering to the condenser increases to this point A, Yes or no? This point A. Okay. And as we are seeing that this temperature rise happened because of the heat transfer of this exhausting fluid. So when it loses its heat, its temperature is going to get decreased. So here we go. We'll having this B point. We'll be having this B point. So this is B. And from here, this will exhaust and will go again to the to the compressor, and we have utilized some heat energy of the exhausting gas from the gas turbine. Okay. Now something obvious I am going to write. I hope you understand this, that TA will be less than equal to T4, and TB would be greater than or equal to T2, Say yes or no? Why so? Because we are, see this fluid, let's say, is entering let's say 1000 degree or 1000 Kelvin, and this is here at 500 Kelvin. So this stream or this line of fluid is giving its heat energy to this. So the temperature rise won't be above the 1000 Kelvin mark. You cannot increase the temperature to 1000 Kelvin mark. And same way, if this temperature is 500 Kelvin, you cannot reduce this temperature beyond this temperature 500 Kelvin. So this is what I have written. This is what I have written. So with the use of regeneration, what is regeneration? In regeneration, we try to utilize. In regeneration, we try to utilize the high heat energy of the exhausting air. We try to utilize the high heat energy of the exhausting stream of air and use that heat energy to reduce the heat addition so as our efficiency can get more. Okay, because now you see if you see, so previously in the ideal cycle we have to raise or we have to add the heat so as to increase the temperature from 2 to 3. Now we only have to add the heat to increase the temperature from a to 3. And as we have already know that this T3, we cannot go beyond this T3 mark, because beyond this T3 mark. Okay, so for given T3, if we apply the regeneration, the amount of heat addition will be reduced. In the combustion chamber. So heat addition reduced means input reduced. So somehow efficiency can be increased. Okay, that is increasing or not, we cannot comment like this. We will see. Now, firstly, tell me this concept of regeneration, or what is the intention? What is the intention behind this regeneration? You are able to get it or not? You are able to get it or not? Tell me, you are able to get it or not? Those who are live in this session can respond to me. Those who are live in this session can respond to me, please. Those who are live can respond to me so that we can move further. Okay, so is that I am considering this to be understood. Okay, I as responded by you guys. Okay, so now we are having this regenerator. Now let's see what will happen. What will happen to that T mean? So Pawan, T mean, you are asking T mean will increase or not, that we are going to see. But you have to correct your question also. That's what will happen to the mean temperature of heat addition and what will happen to the mean temperature of heat rejection. What will happen to the mean temperature of heat rejection? Okay. So if you see the original cycle is 1, 2, 3, 4, 1. This is the without regeneration cycle. And if we talk about with regeneration cycle, our cycle will go like this: 1, 2, A, 1, 2, A, 3, 4, B, and 1. All right. So this is 1, 2, 3, 4, 1. So if you observe the heat addition in this process, in the ideal cycle, in the without regeneration cycle, so you will say, sir, mean temperature of heat addition would be somewhere in between 2 and 3. So this black pen represent that TMA1 of ideal cycle. Okay. And if you say in the regeneration cycle, the heat addition is taking place between A and 3. The heat addition is taking place between A and 3 in the combustion chamber. So what is happening to the mean temperature of heat addition? So the mean temperature of heat addition is increasing, as you can see with these marks. Okay. So with regeneration, what are the effects? With regeneration, effects, what are effects? What are those effects we can see? What are the effects we can find? So what effects we can conclude that with regeneration, TMA increases. All right, TMA is increasing. And with regeneration, if we talk about the mean temperature of heat rejection, so you can see from 4 to 1, this is TMR1. So as we have established that the mean temperature will be somewhere in between Mean temperature will be somewhere in between 4 to 1. So let's say our TMR1 is this. And in the regeneration cycle, our heat rejection is taking place from B to 1. So our mean will come somewhere in between B and 1, somewhere in between B and 1. So we can say our TR2 is this. So can we say that our TMR, mean temperature of heat rejection, is decreasing? So what we have established that whenever mean temperature of heat addition increases, mean temperature of heat rejection decreases, our efficiency can increase without changing the pressure ratio. Without changing the pressure ratio. Got my point or not? Got my point or not? Say yes or no. Say yes or no. Say yes or no. So when we go to the actual cycle, there is actually some pressure loss associated. So for that, first let us understand completely this ideal cases. So with the regeneration, what happens? Our mean temperature of heat addition increases, our mean temperature of heat rejection decreases, and so our efficiency increases. So if I write the efficiency with regeneration. If I write the efficiency with regeneration, so regeneration efficiency is turbine minus compressor upon heat added. So you have to see no formula is needed to be required to be learned or memorized if you have your basics right. So our turbine work is nothing but T3 minus T4 CP T3 minus T4. So let's just write it. So CP will be cancelled out. So I am writing just in terms of temperature. So it will be T3 minus T4 because this C, our expansion. Yes, you are asking, sir, do regeneration give best efficiency in Brayton as like in Rankine over other methods? So yes, regeneration is a process of increasing the efficiency. So if you are using your cycle with regeneration, definitely you are going to get the better efficiency. The better efficiency. If you further cases, you will find that with intercooling only our efficiency reduces. Our reheating only our efficiency decreases. But if we combine the regeneration, reheating, intercooling all together, the overall efficiency will increase. So regeneration always strives to increase the efficiency of the cycle. Okay, and same so happens in the steam turbine cycle also. Although there cannot be any heat exchangers, separate heat exchanger there. So we do regeneration in steam turbine cycle with the help of open feed water heaters or closed feed water heaters. If you have learned those cycles, okay, if you have learned those cycles, you will be able to understand those. Okay, we do not use this kind of heat exchanger in steam power cycles, but we use the open feed water heater and closed feed water heaters there. Okay, all right. So we are writing the turbine equation. So it is between 3 to 4. So H3 minus H4. So if I convert it in terms of temperature, it will become T3 minus T4, and compressor will be become T2 minus T1. So there is no change, as we can say, as we can see, there is no change in the compressor work and in the turbine work, in the compressor work and in the turbine work, but the heat addition changes. Heat addition changes to heat addition changes from T3 minus TA. Heat addition changes from T3 minus TA. So previously it was from T3 minus T2. Heat addition was T3 minus T2, but now it is what? But now it is, just a second. So but now it is what? It is T3 minus TA. It is T3 minus TA. It is T3 minus TA. Got my point or not? Got my point or not? Okay. Okay. So now in order to have the efficiency, we can make a formula here also, but that is not required. You can do it by your basic concepts. You can do it by your basic concepts also. You can do it by your basic concepts also. Okay. Now see. In order to find this regenerator efficiency, in order to find your regenerator efficiency, sorry, efficiency with regeneration, you realize that, sir, we require this TA. We require this value of TA. So for that, we will apply some concept of heat and mass transfer. There is a topic in heat and mass transfer. There is a topic in heat and mass transfer known as heat exchanger. Okay, so we will apply some basic concepts from there. We will apply some basic concept of it. So we have this one, we have this one, let's say, and we have this one, we have this one. And this is the heat exchanger we are using above, where this is the flow of the hot fluid, where this is the flow of the hot fluid. Yes or no? This is the flow of the hot fluid, all right, and it is exiting at this point B, and this is the flow of the cold fluid, which is entering at 2 and exiting at A, exiting at A. So we have seen a term known as effectiveness of heat exchanger in the subject heat and mass transfer. In the subject heat and mass transfer, so let's say this epsilon is the effectiveness, this epsilon is the effectiveness of the heat exchanger. So we can write like this, that this effectiveness is T4 minus TB, or we can say, what is this effectiveness? This effectiveness is actual heat transfer upon actual heat transfer. So actual heat transfer, because A is greater than 2, so we must write like this: actual heat transfer is TA minus T2. Okay, this TA minus T2, okay, if mass flow rate we consider same, is equal to this T4 minus TB, but we require to find the TA, so why to unnecessary firstly calculate TB? We do not have any use of TB for now, so we can have the value of TA. Okay, so that's why I'm writing this equation in terms of TA upon maximum possible heat transfer, maximum possible heat transfer. So from here you can say this is the relation of our effectiveness. So if if the effectiveness value is given to you for say 0.8, let's say effectiveness is given to you 0.8, so can you calculate, if you know the value of T1, T2, T3 and T4, that you can calculate by your general concept of isotropic process. So can you say you can find the value of TA? And once you find the value of TA, you can put it in this equation. You can put it in this equation and you can have your efficiency. So if somebody will say that perfect regeneration is taking place, so if someone will say, sir, that we are having the perfect regeneration, so it means that the effectiveness of your regenerator or the heat exchanger is maximum possible. So that is one. So if perfect regeneration is taking place, TA will reach to T4. So TA will be equal to T4 and TB will be equal to T2. So in case of perfect regeneration, you can use TA is equal to T4. So if I write the efficiency, where is the efficiency? This is the efficiency. So if I write the efficiency for perfect regeneration, if I write the efficiency for perfect regeneration, if I write this efficiency for this perfect regeneration thing, okay, we should replace this. Replace what? We should replace this by T4. Okay, we should replace this by T4. So with regeneration, let me call the efficiency as this REG. So can we say like this? Can we write the efficiency like this? So this is not the same efficiency as you have achieved from this ideal gas relation, from this ideal Brayton cycle, from this ideal Brayton cycle. So if you calculate, what? If you apply this, if you apply what? If you apply this, see, T2 by T1, T2 by T1 is Rp to the power gamma minus 1 by gamma, as we are not doing anything with the pressure ratio. So T2 by T1 will be Rp to power gamma minus 1 by gamma. Also T3 by T4, also T3 by T4, also T3 by T4, also T3 by T4 will be equal to, T3 by T4 will also be equal to Rp to the power gamma minus 1 by gamma, gamma minus 1 by gamma. So from this equation, if you want to see, from this relation, if you want to see, so if we in the numerator, if we take T1 as common, and in the bottom we take T3 is common, so this equation will become somewhat like this: T2 by T1, T2 by T1, T2 by T1, okay, T2 by T1 minus 1 divided by 1 minus T4 by T3 divided by 1 minus T4 by T3. Is that true or not? Is that true or not? Tell me, is that true or not? Okay, is that true or not? Tell me that. Harsh, you want me to check heat addition in efficiency, that T3 minus TA. So, sir, we are talking about the perfect regeneration, no? So, TA is equal to T4, TA is equal to T4, TA is equal to T4. So, if TA is equal to T4, that is why I've directly written TA is equal to T4 here. You can write first TA here, then you can replace it by T4. See, this is the efficiency, no? This is the efficiency, that is TA. Okay, so now in perfect regeneration, we have TA is equal to T4. That's why I have replaced it with T4. Okay, so if I take, let's say, if I write like this, is that okay, Harsh? If we further take this T2 by T1 common, it will be like 1 minus T1 by T2, 1 minus T1 by T2, 1 minus T1 by T2 upon 1 minus T4 by T3, 1 minus T4 by T3, 1 minus T4 by T3. So this is the efficiency of regenerator we are solving for. So we can say T1 by T2. Can we say this? Let's see, can we say this or not? T1 by T2 is equal to T4 by T3 is equal to T4 by T3. Yes or no? These two are same only, no? These two are same only, right? So we can cancel this out. This is same only. So we are cancelling this out. So what is our regenerator efficiency with regeneration is coming out to be? So it is 1 minus T1 by T3, 1 minus T1 by T3 into T2 by T1 is what? Rp to the power gamma. Let me write here. There is not much space is left, so I'm writing it again. So let me just erase it and write it again. And going to write it again. Okay. So we have this efficiency with regeneration. We have this efficiency with regeneration equal to 1 minus T1 by T3, and this T2 by T1 is Rp to the power gamma minus 1 by gamma, is Rp to the power gamma minus 1 by gamma. So we are having the efficiency formula with regeneration. We are having this efficiency formula with regeneration, right or wrong? we are having this efficiency formula with regeneration. Is that clear or not? Is that clear or not? So if you observe this relation, so an important outcome we can attain, an important finding or observation we can have from here. Thus, sir, we have seen with the increase of pressure ratio, the efficiency of ideal Brayton cycle, not this cycle. The efficiency of ideal Brayton cycle was increasing. The efficiency of ideal Brayton cycle was getting increased or increasing. The efficiency of ideal Brayton cycle was getting increased or increasing. So if the pressure ratio is increasing, the efficiency of ideal gas turbine cycle or ideal Brayton cycle increase, but the efficiency of this cycle, which is having regeneration, decreases. Okay, so if we increase the pressure ratio, the efficiency of ideal Brayton cycle will increase, but the efficiency of Brayton cycle with regeneration certainly decreases. As we can see from this expression. So regeneration is clear or not? Effect of regeneration is clear or not? With regeneration, we can have what if regeneration is there and we are increasing the pressure ratio, the efficiency is going to get decreased. So is that clear or not? Is that clear or not? Tell me. Is that clear or not? So you can find the questions on it in GATE previous year question, because this is already was there in its syllabus. So why we are teaching it here? Because to describe the actual gas turbine cycle, it is impossible to describe the actual gas turbine cycle, which was not previously in the syllabus. It is impossible to describe that without describing these basic things. Okay? And you can apply the same kind of approach in the steam turbine cycle. If you observe, while discussing the steam turbine, I focused on the equipment of the steam turbine, and here I am focused on the cycle. Because overall, you can apply the phenomena of equipment as a steam turbine as a equipment here on the gas turbine, and the phenomena of the cycle we are taking from this gas turbine cycle. You can apply the same concept in the steam turbine cycle. So overall, the power plant will be covered here. Almost all the power plants, new syllabus, old syllabus, everything will be covered. Okay. So now regeneration is clear. So let us move to the next concept, and I would like to request you to like and subscribe the GATE Academy also. Because if you have watched all the videos of this series of new GATE syllabus edition, you must have thought that we have taught a lot of things in this span of, we are having total number of 12 sessions. So this is the 10th session, and last 2 sessions are left for tomorrow. Okay. So if all these 12 sessions you guys watch, 24 hours you have to spend, all this new syllabus, compressible flow will be covered, gas turbine, steam turbine covered, and maximum part of already syllabus which was there, that help also you are getting. Okay. So now let us move to the next topic. So let us quickly see the intercooling. And then we'll see the reheating. And after then, we will go to the actual gas turbine cycle in the next class, in the next session. So we have intercooling. If we do the intercooling, and we will also solve some question of this ideal Brayton cycle. At least 1 or 2 questions we'll solve, so that this will all be clear. Then we'll see the actual gas turbine cycle, and we'll solve the question of actual gas turbine cycle also. So if we apply intercooling, in Brayton cycle, so as the name suggests of it, so intercooling means what? That there is something like cooling thing, something we are cooling in between the stages of the Brayton cycle, So in intercooling, what we do, just focus over here. So in intercooling, what we do, we use 2 compressors. In intercooling, what we'll do, we will use two of compressor. We will use two compressors. So let's say this is compressor 1. This is compressor 1. So let's say air is entering at this compressor 1 and leaving at this 2. Okay. 2. Then we will have an intercooler. Then we will have an intercooler. What is that we are going to have? So after leaving from this first compressor, we will have our intercooler. So let me call it as IC because it is an intercooler. Okay. So after our air leaves from the intercooler, it will go to the second stage of compression. Second stage of compression. So let us call it compressor 2. Okay. Or you can say second stage compression process or second stage compressor. So after our air leaves this compressor 2, it will go to the compression chamber. I am not taking regeneration here. We are just taking intercooling. So we have this combustion chamber. Okay. And after the air leaves this combustion chamber, where it goes? It goes to the turbine. Okay. It goes to the turbine. And when it leaves the turbine, it will go to the cooler. And then the cycle will complete, because after this cooler, the air will go to the compressor one. And we are considering this cooler for the sake of making the TS diagram and all, and PV diagram, TS diagram and all, PV diagram, TS diagram and all. Why we are doing so? Because generally the gas turbine cycle is open cycle, but for sake of making TS and PV diagram, we are considering it as an open cycle. So those students who are live in this class, I want you to attempt this PV and TS diagram of intercooler, of this Brayton cycle with intercooling. Okay. So intercooler is also a constant pressure device in which, as the name suggests, cooling happens, means temperature reduces. So before I move ahead from this point, I want you to draw the PV diagram as well as the TS diagram. Is that clear? So I'm taking a pause here for 2 minutes, 3 minutes, so that those students who are live in this session can try by themselves, so that this is more clear to you. And those who are watching the recorded session or the video, you are also, if you draw your PV TS diagram before I do, the things will be even more clear to you. Okay? So just try and do it. Try to do it. And also do not forget to subscribe the GATE Academy channel. Please try and solve it. Is that done? Is that done? So very good. If you have done it, this is very good. So now let us make the TS diagram and PV diagram. TS diagram and PV diagram, and now we'll see what are the effects of intercooling. What are the effects of intercooling? So we have this TS diagram. So in order to make the TS diagram, let's just first draw the three pressure lines, because here the play is in between three pressure lines. The play is in between three pressure lines. And in this also you must try that your, because later on we have to do the regeneration also. Later on we have to do this regeneration also. So try to make this special line, in such a way, that the exit point, exit temperature of of the turbine is above the entry temperature to the gas, to the combustion chamber. Okay, so from here what is happening, from 1 to 2, if you see this diagram, from 1 to 2 compression is happening. So applying all the air standard assumptions, so we can say this is 1 and 2, this is 1 and 2 isentropic, this is 1 and 2 isentropic compression. In intercooler, what will happen? Constant pressure heat rejection will be there. So we will come to this point 3. What will happen? In the compressor stage 2? So again your pressure will increase, and you will reach to this point 4. Then heat addition will take place. Till this point 5 in the combustion chamber. Then what will happen? Then isentropic expansion will take place. And after then heat rejection will take place. So do try to make this point 6 above this 4. Above this 4. Okay, so I just have expanded it a bit, so that if you are not, because I thought it is getting little too small. So now I think you can comfortably see it. Okay. So now from 1 to 2 isentropic compression is happening. From 2 to 3 constant pressure heat rejection is happening. Taking place. From 3 to 4, what is happening? Isentropic compression is happening. Okay, and then 4 to 5 constant pressure heat addition is happening. So that temperature and entropy both are increasing in the combustion chamber, as usually it happens, and we reach to the point 5. Okay, then from 5 to 6, what will happen? Isentropic expansion will there, so we'll reach to point 6. And as you can see, I tried to make this point T6 above 0.6, temperature of 6 above 4, because we will be adding regeneration here also at later point of time. So just make this habit, otherwise you will have confusion increase. Okay, so the live student can respond who has made the correct TS diagram. Those who have made mistake can mention that, sir, yes sir, we have made a mistake. If you have not made a mistake, it is good. So now we are going to draw the PV diagram also. So now let's see one thing. So what is the intention of doing intercooling? And later on we'll see. I will try to cover it in this session only, if we can cover it quickly. So if we see in intercooling, so later we are going to see the reheating cycle also. So the purpose of the purpose of intercooling and reheating both, is to increase the network done. So the purpose is to increase the network done. So the network done is turbine work minus compressor work, turbine work minus compressor work, turbine work minus compressor work. So in intercooling, the compressor work decreases. The work in a compression, and obviously we are talking in comparison with the cycle in which intercooler has not used, is not getting used. Okay, so this what we can say, with the use of regeneration, the work required in the compressor, the work required by the compressor certainly reduced. So now we are going to see how this is happening. So we have a compressor, say 1 to 2, say 1 to 2, 1 to 2. Then we have a constant pressure intercooler, so heat is getting rejected in a constant pressure intercooler. So has in constant pressure heat rejection process, what will happen? What will happen in constant pressure heat rejection process? That our volume decreases, at constant pressure, our volume get decreases at constant pressure, and from 3 to 4, what is going to happen? From 3 to 4, we have a second stage compressor. So we are going to reach till this point. From 4 to 5, we have constant pressure heat addition. From 4 to 5, we have constant pressure heat addition. And from 5 to 6, we have isentropic expansion. So we will reach 5 to 6. Okay, 5 to 6. Now 6 to 1 is constant pressure heat rejection. Now, if you understand, if we do not use intercooler, or if we do not compress in two stage, so what we were doing generally, that we were compressing to this low temperature directly to the low pressure directly to the high pressure. So this is let's say what is this? 1 2-561 is Brayton cycle without intercooling. I think you are able to understand this, that if we do not use intercooling, 1 2-561 is Brayton cycle without intercooling, or without we can say that without compressing in two stages. So obviously we are compressing in one stage. Okay, in one stage. So you require what you say, that sir, if we compress from 1 to 2 dash directly, this much work will be required, because you know from our general thermodynamic concept that work done in an open system is minus VDP. So if we want to get the work done in an open system, we have to find the area under the curve when projected upon the pressure axis. In closed system, we project on the volume axis, but in open system, and as compressor turbine, all are open system devices. So if we want to find the work in this process, we need to project it on the pressure axis. So let's say this is the work required by the compressor in case we compress in one stage. But now as we are compressing from 1 to 2, so in 1 to 2 in 1 to 2 till 1 to 2, this much work will be done. Till 1 to 2, this much work will be required. And from 3 to 4, this much work will be required. So can you understand that we have saved this highlighted reason? We have saved this amount of work while this amount of work while compressing in two stages and with the use of intercooler. So this is the saving of work. This is the work saved. This is the saving of work. Yes or no? This is the work we have saved while compressing in two stages. Yes or no? Compressing in two stages. Can you understand this or not? Okay. So by intercooling, we reduce the amount of work required by the compressor. We reduce the amount of work required by compressor, and hence some saving of work is there. So our network output certainly increase. Our network output certainly increase. So how we reduce the compression work required in compression, and how our network then get increased. This is clear from the intercooling part. This is clear for the intercooling part. Now coming to the efficiency part. So let us compare. So we have this. If we do not do intercooling, we have this cycle. Let's say 1 2 dash 561 1 2 dash 561. Yes or no? If we do not do the intercooling, we do compression in a single stage, as we were doing in the cycle. So we have this 1 2 dash. We will have this 1 2 dash. Our pressure will directly be increased till this point. So in this, what was the mean temperature of heat addition in the cycle without intercooling? So in the cycle without intercooling, so this is the TMA. I have made it with black ink, and let me highlight it also. So this is the mean temperature of heat addition in the original cycle without intercooling. So if we do the intercooling, now with intercooling, our heat addition is from 4 to 5. So a point somewhere in between 4 to 5, so we can say that our TMA2 is somewhere in between. Somewhere in between this point. So this is our TMA2. So what has happened? With intercooling? What effects of intercooling we can say from this? That with intercooling, compressor work decreases. We have seen this, but we are also now seeing that the mean temperature of heat addition also decreases. Okay, now let's say what will happen to the mean temperature of heat rejection. The mean temperature of heat rejection. So in the original cycle, the mean temperature of heat rejection is here. I am making it with the green pen, between 6 to 1. All right, between 6 to 1. Between this, I have highlighted. So this is our TMR1. This is our TMR1. Okay, mean temperature of heat rejection. Between 6 to 1. Okay. Now, if I see the intercooling cycle, some people may get confused. Sir, with the intercooling also, this is going to remain same. So I want to tell you, this is not going to remain same. Why it is not going to remain same? Because if you observe in intercooling, the heat rejection is taking place between 2 and 3 also, no? So we have this 2 and 3 also, and we have this 6 to 1 also. So heat rejection is taking place at those two places. So if you take average now of these two, so certainly this TMR2 is also going to get decreased TMR2 is also going to get decreased. So Vijay, this is not same. This is not same, but mean temperature of heat rejection will also decrease. Mean temperature of heat rejection is also going to get decreased. Okay. Okay. So what will be the effect? What will be the effect on the efficiency? Because we have seen if TMA decreases, the efficiency decrease. The effect of it is the decrease of efficiency, and the effect to it is increase of the effect of it alone is increase of efficiency. Okay. Okay, so what will happen to the overall efficiency? What will happen to the overall efficiency? So in this the mean temperature of heat addition reduces in more dominance. Mean temperature of heat addition reduces more as compared to the mean temperature of heat rejection decrease. So ultimately the overall efficiency with this effect, is going to get decreased. Okay, so this decrease is more and this increase is less. So what is the overall effect? What is the overall effect of intercooling? The overall efficiency is going to get decreased. So what are the effects of intercooling? We have seen that by intercooling the compressor work reduces, so net work increases. By our intercooling, the mean temperature of heat addition reduces. By our intercooling, the mean temperature of heat rejection also decreases. But overall the efficiency decreases. Okay. So now we have seen till this session about the intercooling of Brayton cycle. So if you want to find the efficiency, with intercooling, just apply your basic concepts. So your turbine minus compressor upon heat addition. Okay. Upon heat addition. So let's just do it from our basic concepts. If we know that turbine work is from 5 to 6. So in terms of temperature, I am writing. So this is going to be T5 minus T6. This is going to be T5 minus T6 minus this compressor work. So compressor work is taking place at two places. So from 1 to 2, so that is T2 minus T1. From 3 to 4, so that is T4 minus T3. That is T4 minus T3, and your heat addition is going to be from T5 minus T4. So this is the formula for efficiency. If only intercooler is applied. So as you can see from this formula that we cannot certainly memorize all the formulas. So the better thing is to go with the basics. So whatever is coming is coming. Okay. And if somebody will use this word perfect intercooling, as there was perfect regeneration, there can be also perfect intercooling. Okay. So in perfect intercooling, what will happen? What changes will happen? That this T1 and T3 are going to get equal. T1 and T3 is going to get equal. So if T1 and T3 is going to get equal, the pressure ratio between their stages means if I say the pressure in between this stage is Pi, intermediate pressure, this is the pressure ratio is also going to be same. Because as T1, T3 is equal. So something like that will happen. And just applying by T1 is equal to T3, you will have all your results. And definitely when you do the perfect intercooling, your overall compressor work will be minimum. Your net work done will be maximum. Okay. So if somebody will say perfect intercooling, just use T1 and T3, all the results will come. Nothing else to remember. So if there is a doubt, if there is any doubt in this session, you may ask me, those who are live in this session. So we are going to see in the next session, because as we were not able to complete the reheating, reheating cycle in this topic, in this session, we are going to conclude. firstly in the next session, that is tomorrow at 10 a.m. Okay, at 10 a.m. So tomorrow we'll be ending this series by finally uploading the next two sessions. So if you come live, that will be much better because you can ask your doubts as well. Okay. Okay. So in the next session, we are going to see the Brayton cycle with reheating. Then we are going to see combining all these things: regeneration, reheater, intercooler, and we'll try to see some numericals on it. Then we will move to the actual gas turbine cycle. So in the next session, we are going to start with the we are going to begin the actual gas turbine cycle. Okay. So if there is any doubt, you can ask me, and do subscribe the Gate Academy channel. So as you are not asking any doubt, so I am signing off. So thank you very much. Thanks for watching the video. We are going to have two sessions left, so do watch them also. Harsh, which is the last slide you want? Last slide you want to see? Which last slide you want to see? This one? Just wait a minute. So you have a doubt, so we are waiting here. This one you want to see? This one? Is there a doubt, Harsh? Is there a doubt, Harsh? Can you tell me what doubt you are having? Yes, I said efficiency decreases when mean temperature of heat addition decreases and increases when mean temperature of heat rejection decreases. We have this Carnot efficiency, no? Cleared? Cleared? Okay. If it is clear, then we can move ahead. So thank you very much. I would like to say bye to all of you. Thanks for watching the video. Thanks for watching the video. And if you have any query, any feedback, any suggestion, do visit thegateacademy.com and send us your feedback about this video, about the session. You can suggest us. Okay, you can have the information about the upcoming courses, about the admission thing, about everything on the gateacademy.com. Okay. Okay. So thank you very much. We will see each other in the next session. Thank you.